In this question, we are testing a claim about some mean value. Here it says the claim is that a smartphone carrier's data speeds at airports is 13 megabytes per second. So I'm going to go ahead and write down my null hypothesis and my alternative hypothesis. So the claim is that the mean value for all smartphone carrier data speeds is 13 megabytes per second. So that means that the alternative hypothesis is that that mean value is not 13 megabytes per second. So that means that it could be less than 13 or greater than 13. And I'm going to keep track that this is the original claim. So to test this claim to see if that is true or not, we need to collect some sample data. So in this particular example, our sample data consists of us looking at, let's see, 26 different cell phone speeds. And from those 26, the only other information that this problem gives us is it gives us a test statistic. So notice that this problem does not give us the average speed for those 26 smartphones, and it doesn't give us the standard deviation. So the reason why I mentioned this is because typically if you have the sample size, the mean for your sample, and your sample standard deviation, then on our calculator, we can use a t-test. And the reason why I'm using a t-test here is because the population standard deviation is unknown. So we're always going to use the t-distribution. Okay, so if we were to use the t-test on our calculator, we would put in n, the value of n, x bar, and s, and then a t-test on the calculator. It will give you two pieces of information that are really important to help us test that claim. So it's going to give you your test statistic. Actually, let me use black here. It's going to give us our test statistic, which in this problem, that test statistic is going to be a t-score or a t-value, okay, because we're on the t-distribution. If we were on the normal distribution, it would be a z-score. So it behaves in the same way. And then the other piece of information it's going to give us is it's going to give us a p-value, okay, and your calculator is going to show it as some p equals. Okay, so in this particular problem, what we're given instead is it seems like they've already done the hypothesis test. They've already done that t-test. And they tell us that our test statistic, our t-score, is 2.009. Okay, so what we need to do is we need to figure out, so our test statistic is 2.009. We need to figure out what is the p-value that corresponds with that test statistic. So let me explain first what the test statistic is. This is a vocabulary word you want to make sure you're familiar with, and then that will help you understand what a p-value is. So the easiest way for you to understand this, and I think, in my opinion, is to take a look at a graph of the t-distribution. So notice that the t-distribution, it is also bell-shaped, very similar to the normal distribution. At the center of your t-distribution, you're going to find your null hypothesis value. So here, that null hypothesis value is 13. So mu naught is 13. So basically what this bell-shaped curve is it's a sampling distribution of sample mean. So it consists of a whole bunch of different x bars where each x bar is a sample mean for every time that so basically every time that you get a sample of 26 cell phones, you could potentially get a different sample mean value. And so we can create a distribution for all the different ways that you can calculate the average speed on 26 cell phones. And so we learned about this concept in section 6.4 when we were looking at sampling distributions and the central limit theorem. And so again, it is bell-shaped. So we learned that sampling distributions for sample means are bell-shaped, which means that there is different probabilities that correspond to different x bar values. So what we want to know is we want to know the x bar value, which here it's unknown, but we want to know our x bar value for our sample of from the 26 cell phones that we looked at. Where does it fall on this bell-shaped curve? So where does it fall on this sampling distribution? If it falls close to the mean, so let's pretend that it's this x bar, then that means that this value, all right, so the sample mean for our sample here is pretty close to that null hypothesis value. If it is close to that null hypothesis value, it's going to occur at a higher probability. And so in that situation, we would say that the difference that we see in this in the average speed, right? We see that there's a difference, but that's really just due to sampling error. It's not due to the fact that the mean value is actually some value other than 13. But let's suppose that our x value lies in the tail of the distribution. So here, because our test statistic is 2.009, it actually indicates that our sample mean value is in the tail of the distribution. So it probably lies closer in the tail here, where you can see that this distance is much further away from that null hypothesis value of 13, indicating that the average data speed is probably some value greater than 13, meaning it's not 13. So on this t distribution here, every single cell phone speed has a corresponding t-value. So if we're at the center, then that means that that t-value is 0. So you can kind of think of it as it's 0 standard deviations away from the mean. But our test statistic here, which I'll mark in green, so 2.009, is all the way on the right tail. So recall back in chapters like 2 and beginnings of chapter 6, we said that values that have z-scores or t-scores that are 2 or more standard deviations away from the center of the distribution, they're considered statistically significant or extremely high, or we say extremely like unusual. So that is what a test statistic is. Your test statistic is a t-score or a z-score if we're on the normal distribution that tells us how far away our sample mean, right? So how far away is our sample data from the null hypothesis value? So I can actually mark that x bar value, right? So I don't really know what that number is, but I know it lies in the tail. And so here, if I shade in an area that is to the right of this test statistic of 2.009, that green shaded area, this is what we call the p-value. So a p-value is a probability. It is an area under the curve that tells us how likely, right? So what is the probability that we would get some x bar value in our sample that is at least as extreme as the one that we got. And the one that we got has a test statistic of 2.009. So the question becomes, how likely, so what is the probability that we would get this specific sample mean or some value larger than that? So because it is an area on your calculator, you can use the function TCDF to find areas under the curve under the t distribution. So the information that TCDF is going to ask you to put in is a lower limit. So here that lower limit is going to be 2.009. And then your upper limit, because remember this is like a continuous function, so you just need to put in a really, really large value. So you can either put in 1E99, or that's the same thing as 999,999. So I'm going to just type in 1E99. And here, the next thing that your calculator is going to ask you to type in is your degrees of freedom. So for this particular problem, because n is 26, my degrees of freedom is going to be 26 minus 1, which is 25. So when I type that into my calculator, and I didn't do this ahead of time, so let me just go ahead and do this real quickly. I'm going to go to second bars in my calculator to take me to the distributions, choose TCDF. I'm going to type in my lower limit of 2.009, upper limit 1E99. My degree of freedom is 25. And so this gives me a probability of 0.023 if I'm rounding to 3 decimal places. So because this is a two-tail test, and how do I know that it's a two-tail test? I look at the alternative hypothesis, which has that not equal sign. So actually, because I have a two-tail test, this area that I shaded in green, I know before I said it's the p-value, but it's actually your p-value divided by 2. So it's half of your p-value. The other half of your p-value, you're going to find it on the left tail. So this is always the case when you have a two-tail test. So on the left-hand side here, the test statistic that corresponds to the t-score that separates the green region and the left is going to be negative 2.009. And so here I have an area on the left of 0.023. On the right, this area right here is also 0.023. So that means that my total p-value, I have to take 0.023 and I have to multiply it by 2 to get the p-value. So 0.023 times 2 means that the p-value is 0.046, indicating that there's an approximately 4.6% chance that I would have gotten the sample mean that I've gotten for my sample, all right, or some value greater than that.